Oh, sorry, I should not see the answers. Yeah, so in chapter exercise 2, so first question, show that the quotient of the middle term in this thing is equal to the sum of the coefficient of the two terms in the expansion of this guy. So the two middle terms in the expansion of this, okay, those will be like 2n plus 1c, so coefficient of those, right? So 2n plus 1c n plus 2n plus 1 c, well, n plus 1, which is the same thing as 2n plus 1 c n. So two times of this basically. So you're saying this sum is equal to the coefficient of the middle term of 1 plus x power, right? That's 2n, right? And that's 2n plus, what kind of, what is this? No, that's not correct. It can't be correct. So you're saying this is equal to 2ncn? No, no, that's not right. It's like 2 times of, oh, this is like n plus 1, right? So 2n plus 1 upon n plus 1, that times of 2ncn is equal to 2ncn. No, that's not always correct. So this is wrong, I guess. Okay, let's search for a counter example. So let's say n is equal to 1. Then this 1 plus x power 2, that will just be 1 plus 2x plus x squared. And then when n is equal to 1, this thing will be 1 plus x power 3, which is just 1 plus 3x squared plus x cubed. And you can clearly see that this plus that is 6, which is not 2. So first question, I mean, this is wrong, basically. Okay, so first wrong question. Okay, cool. Second, find the greatest term in the expansion of this guy. Oh yeah, so let's do the same thing as we did in the last video. I showed you how to find the greatest term. Now I'm going to show a practical of how to do it. So your a value, which is just n plus 1, so it's going to be 21 upon 1 plus mu. In this case, mu is just square root 3, right? So first term upon second term, so square root 3. 1 plus square root 3. Yeah, so you would actually like a decimal representation of this. So first of all, let's rationalize this guy. So 21 upon 2, and that times square root 3 minus 1, right? Square root 3 is 1.7 something, so this is going to be 0.7, and that times of 10.5 something, whatever. So you can say slightly bigger than 7, yeah, because this is almost 10. Okay, well, I can just do it. So 7.2 maybe something. I don't know. I don't remember the whole value of square root 3, but it was something like this as far as I can remember. Yes. So this would be 7.2 plus, so half of it basically, so 0.36, and that would be 7.56. So somewhere around that, which is just some integer. So yeah, something just slightly bigger than 7. So that means the floor function of that. So 7 is basically the value, right? I mean, you only get 2 terms when this thing somehow becomes integer. If it's not, just take the floor function. That's the r value. So r value is 7. So just 220c7. Then you got 1 upon square root 3 power 7, which is like 1 upon square root 3 power 6. And that times 1 upon square root 3. So this would be power 3, and then this is gone. So 1 upon 27. And then that times square root 3. So this cancels. You just get 27 upon 27. Okay, let's go to 3. So third is find the greatest term in the expansion of this, where x is equal to 2 upon 3. Once again, if you gave us the x value, why do you want to expand this? But let's do it. Okay, so greatest term. You know, they only told about the greatest, I mean the numerical greatest term, right? So thing is, this is going to be 7 minus 10 upon 3 power 11. So all of these odd terms, so odd r terms, which is even terms actually, those would in fact be negative. So they already have disqualified as being the greatest terms, right? But then if we are talking about greatest numerically greatest term, then those can also be considered. But yeah, whatever. So let's try it out. So once again, just n plus 1, 12, and that upon 1 plus mu. So mu would be 7 upon 5x, which is 7 upon 10 upon 3, which is like 21 upon 10. So 12 upon like 3.1, whatever. So that's something less than 4, so 3 point something. So floor function of that is 3. So r is 3 basically, right? So we just want the third term. Sorry, the fourth term, because actually r equal to 3 means that. Yes. Okay, and you want to find the greatest term. So wait a second. The third term will be negative. So then, I mean, the actual greatest term will be either second or fourth term, but hey, come on. This is just basic level, so you have to put something like something silly so that we get a correct answer, right? But you know what? We'll do it both ways. So first of all, we'll just find out what the fourth term is, that is r equal to 3 term. So that will be 11c3, and then you got 7 power 8 minus 5x power 3, so that you just got negative, but we'll ignore that. This 5x power 3, so 5 power 3, and then you got 2 third power 3, so 2 power 3 upon 3 power 3. This thing, the 11c3 is just 11 into 10 into 9 into 8, and that upon, well, 3 factors are 3 to 2. So this cancels, you get 4, you get 3, so 12, you got 120 times 11, 1320 times all of this stuff. I'm just gonna leave it like that. So it could either be this thing, 1320 times, well, 7 power 8 times 5 power 3, and that times 2 power 3 upon 3 power 3, or it could be either the fourth or fifth term. Sorry, the r equal to 4, or what am I saying? R equal to 2 and r equal to 4, right? Those terms. So let's figure out the r equal to 2 terms should be. It's supposed to be 11c2. Then you got 7 power 9. You got 5 power 2 and then x power 2. And then the fourth term is just 11c4, 7 power 7, I guess. Yeah, that's the thing. Then you got 5 power 4, because the r equal to 4 thing, right? So you got x power 4 over there as well. The best way to compare is just to take a ratio. So we'll take 4 to 2 and see if it's bigger than 1. I guess it might be. So like x squared, 5 squared, 7 power negative 2. And you got 11c4 upon 11c2, which is like 11 into 10 into 9. So what's 11c4? 11 into 10 into 9 into 8. That upon 4 into 3 into 2. So yeah, and that divided by 11c2 is just 11 into 10 upon 2 simply. So this cancels, you get this thing. So like that's 2, that is 3, so it's just 6, right? So this times 6, that should do it. Oh, and also x squared. So did I? Yeah, I already included that, so I'm going to do that once again. So x squared, that's just 2/3 squared, right? So it's supposed to be, yeah, it's 2/3. So this will be like 10 squared, 100, and that upon 9, I guess. So 9 into 49, and then you got 6 over here. So this will be 2, and you got 3 right there. So it's supposed to be 200 upon 1218, so 138, whatever. So that's the biggest term, right? So the bigger term is, of course, the r equal to 4 term. Yeah, so this quantity. Right, so I mean, let's not calculate it, so just leave it like that. So second, the actual answer, that should be 11c4, 7 power 7, 5 power 4. Yes, x power 4. Yeah, that's what you think. This is the beginner answer, this is the actual answer. Okay, let's go to the fourth one. Given that the fourth term in the expansion of, this expansion has the maximum numerical value, find the value of x for which this is true. So once again, the same thing, figure out what the a value is. So it's just going to be 11 upon, so just look out for mu, right? So it has the numerical greatest value, right? So we just take mod x over here. But mu will just be 2 upon 3/8 of x. So 16 upon 3x. And over here, it should be mod x, but I'm just going to write x everywhere. and whatever positive range we get, just gonna make that opposite so that it works out, whatever. Yeah. And right, this is a thing. So a minus 1 is between r and it's the fourth term, so it's supposed to be r is equal to 3, and then it's less than the same thing over here, 11 upon 1 plus 16 upon 3x. Let's take each of these inequalities side by side and let's see what we get. So solving this, you just get 11 bigger than, and it should be strict inequalities, right? Because you only got one term exactly. Yeah. Wait, but what if this is not the case? I mean, what if you get fourth term and fifth term, or fourth term and third term as the greatest values? Then, but okay, that would invalidate the whole thing, because that would not be greatest. That would be one of the greatest then. So we just solve these strict inequality, and we'll see what we get, right? Yeah, that should do it. So it's just going to be 3 plus 16 upon x, right? 16 upon x is, in that case, less than 8. So x should be bigger than 2, it seems. Okay. Let's also solve that inequality. So erase all of this. Whatever, x is bigger than 2, or mod x bigger than 2, because actually we should take mod x, whatever. And then this will be, then goes over here, just comes 4 is bigger than 11 upon 1 plus 16 upon 3x. So then it just becomes, well, yeah, like 7. So 64 upon 3x is, that's weird. This is bigger than, yeah, it should be 11 minus 4, so it's 7. So that just means 64 is bigger than 21x. So x is less than 64 upon 21. So yeah, there we go. You got a positive range, which is going to be 64 upon 21 and 2. And then you just make this to be negative as well, because you just, I mean, yeah, like numerical greatest. So most likely that's the answer. There could also be the side cases where this value somehow turns out to be an integer, and then you have to do all that stuff. But let's ignore that, because yeah. So there we go. X belongs to negative 2 to 64 upon 7. Wait, 64 upon 21. It's less than that. Sorry. It should be, in that case, 2 to 64 upon 21. So yeah, I mean, this is bigger than 2, right? So then it will be negative 64 upon 21 to 2, negative 2 union 2 to 64 upon 21. That should do it. Okay, so now you got the range for x. Delete this. Now let's go to fifth. Only 5 questions over here. Show that the greatest term in the expansion of this has also the greatest coefficient. Then this, what? Oh, so if the greatest term, grammar. Fine. So the greatest term in the expansion of this guy, we can't figure out that directly. So if it also has the greatest coefficient, well, the one with the greatest coefficient, which is the middle term, which is the r equal to n term. Oh, so that means like n is less than a, so it is the greatest term, right? Yeah. And also it's just only one term, so it must be just one. So n is less than a, and a is, well, what's it? It's just 2n plus 1 upon 1 plus mu. So 1 plus 1 upon x. For now, I'll just deal with it like mu, right? Okay. First of all, we have this inequality. So it just tells us like n plus mu n is less than 2n plus 1. So that just means, this cancels. So mu is less than n plus 1 upon n. And then you also have, well, this thing is actually less than n. Okay, sorry. Yeah, this thing is bigger than 2n plus 1 upon 1 plus mu, whatever. And then minus 1, right? Exactly. So this will be like, okay, 2n plus 1 is less than n plus 1 plus n plus 1 times mu. So n is less than n plus 1 times mu. So mu is bigger than n upon n plus 1. That should do it. And now, since mu is just 1 upon x, just take the reciprocals of these. So, and what do we have to prove though? This Yeah, just take the reciprocals, it's automatically proves, so it's less, it's bigger than n upon n plus 1, it's less than n plus 1 upon n. Cool. So there we go, we did it. Fifth is done. Sorry. So all five done. Let's see the answers. So first is not even, of course. Okay, second, because first is a proof question and also a wrong question. Second is 20C7 and what's this? It's dot 1 upon 27. Exactly, that's correct. Then third is, huh? Oh, okay, they calculated the whole thing and they only have x squared and x power 5. Wait, what? But this is x cube and x power 4. How did they get x squared and x power 5? That can't be. Yeah. And why do they have two things? While really you should just have one of these two things, right? Not two things together. That's not correct. Okay, whatever. So this was wrong. Uh, Either they are wrong or I am wrong, whatever. But, well, I don't think this should be wrong. Okay, whatever. Next question. And then fourth. So, yeah, exactly what we got. So, less than or equal to. So, even equal to works, huh? I mean, no, actually, it should not. Because it is the greatest. And then if it is equal, then you will get some other values as well. So, this should not be like that. But, I mean, fine. As long as it saves your vote. And the fifth was just a proof questions. That's not here. Okay. Then we have binomial theorem for any negative or rational index. So basically 1 plus x power n is equal to, right. So now we are going to the general binomial theorem. This is in fact general binomial theorem, right? So I will just introduce some new notation to you. So I will say that nc0, we already know that's just 1, right? nc minus, I know that looks weird, but nc minus 1, that will be n oh sorry, that's not the way to do it. Yeah, no, we should not do it like that. So nc 0, I mean it's good enough for like in positive integers, right? But for any number, right? So for example, if you have like negative 1c0, that is also defined as 1. We'll do that, okay? We'll define it like that. And negative 2c, I don't know, 1 or something, that will be negative 2 into, just as we do it, n minus 1. So negative 3, and that upon 2 factorial, sorry, 1 factorial in this case. Yeah, well, it's, oh, so it's just 1, sorry. Then it's just negative 2 and then just single, yeah, just single, negative 2. And then negative 2c2, that will be negative 2 into negative 3 upon 2 factorial. So before you couldn't do like 2c3 or anything, that would be 0. But in this case, you can do negative 2c3 as well. So it's going to be negative 2, negative 3, negative 4 upon 3 factorial, right? So it will keep on going. And this also works for, you know, rational numbers. So you could just have negative 2/3 or anything over here. So with this new notation, now we are ready to solve some stuff. Okay. And I mean, I don't know if this actually works with, I mean, if the identities work with these numbers, but I guess they should, right? Yeah, whatever. Let's see. So, yeah, whatever. That's this general binomial theorem. And what are these important notes? NCR is defined only when N and R are both are whole numbers. Yeah, really. We can define whatever we want, all right? I'll define it for negative numbers. What are you gonna do, huh? If n is a negative integer or a fraction, then NCR will be written as this thing. Oh, okay, so you are actually defining with that. Yeah, okay, I understand that. Then why did you say it's not defined for it? We can define it, okay? If n is a negative integer or fraction, then the number of terms of the series are infinite. Hence, if the series hence the series never terminates. Of course, like infinite series, I got it. The first term is not 1, then make the first term unity the following way. Yeah, I mean, that's actually not always you. I mean, okay, you can do it. Of course, you can. But fine, fine. It's okay. No problem. I will do that. If x is so small that the that square and high powers can be neglected, then yeah, so the general binomial theorem can be used for approximation. In fact, it's not doable combinatorically. You cannot actually prove it like that. Instead, you have to go to Taylor series and all that stuff to actually write out a proof for this. So it's really just a Taylor series. Yeah, so it's a Taylor series of 1 plus x power n, nothing else. Right, so if you want to do it, write down a Taylor series for it. You will see the pattern is exactly the same as this. Okay, so really it's just a kind of like approximation, except that it goes to infinity and then it becomes an actuality. It becomes what it is actually, right? But if you just terminate till some terms, that's it. It's gonna be an approximation. Okay, you want some kind of illustration. I mean, general binomial theorem is something that I really use a lot. So, not just in maths, but also in physics and everything. So, you do need to know it. Okay, so let's go to algebra exercises now. Okay, if y is equal to x minus x squared plus x cubed minus x power 4. I mean, that's just a geometric series. You don't even need, the proper thing for that. So, really, it's just okay, so what do you have to prove? You have to prove that x is equal to fine, we can do this. So this is just a geometric series, it's just x upon 1 plus x. That's equal to y. Yeah. So find out what x is. So it's gonna be x is equal to y plus xy. That just means y is equal to oh, we already know what y is, sorry. We just need x. So x will be y upon 1 minus y, which is just y into 1 minus y power negative 1. And then why are we even doing this? You can just write this as a geometric series directly without actually having to go for binomial theorem. So it's just y plus y squared plus y cubed and so on, right? Yeah, this was easy. It didn't even require the GBT. It's just a geometric series. In fact, for any arithmetical geometric series, you can just do it without GBT. But yeah, sometimes you just have to find the quotient of x power n in the expansion of this. Ooh, this is really bad. X squared minus 4x plus 3. You want to find the quotient of x power n in this expansion. Oh no. There's a general binomial theorem, not a general multinomial theorem. We don't know what that is. So you'll have to do the other way. So it's gonna be x minus 4 power 1, and then you got, you know what? No, let's do it the other way. So 4 minus x power negative 1, and then you got 3 minus x power negative 1. You want to find the quotient of x power n from this. Oh no, this is going to be really bad. Okay, think about it. You can't just take n derivatives. That's just not good. Quotient of x power n in the expansion of this. How would I do it? I mean, if it was just like normal, just 1 upon 4 minus x or something like that, it was so much doable. But now that it is like this, how do I do it? Damn, this is bad. So it's just 1 upon 12, and then you got 1 plus x upon 4 plus x upon 4 squared and so on, right? Okay, maybe it's not that bad. Then you got 1 plus x upon 3, and then yeah, like x upon 3 squared and whatnot. Huh. Wait, okay, and now I understand what's happening. So whenever you will have like x power n, what will be happening is that you will have some term from here, some term from here. You will multiply those together. The powers of those terms must. Oh, okay, now I understand. Instead of looking at the brackets, you could just look at what the brackets are providing, right? So either you could have x power 1 or x power 2 or x power 3 or so on, right? So first guy actually gives you I don't know, x upon 4 power m, and this other guy gives you like x upon 3 power n. Yeah, right. Yeah, and this is going to happen in so many different ways that you can get x power m and x power n. You're gonna get in so many different ways. Exactly. So what I'm thinking of right now is something like this, that you have m plus n, whatever the number is, right? So the sum, I should say this like p and q. So you have p plus q is equal to n. Okay, so you have n. Yeah, things you just want to break it into two things. So p plus q, right? And then once you have that, what you want to do is yeah, right. You want to do this thing. So x upon 4 power p, x upon 3 power q. That's one thing. And then you could do x upon 4 power. Oh, you could just start writing it down. Why not? Of course, you can just start writing it down. Oh, this is going to be some weird thing. So you're gonna start off at n, and this will be 0. Okay. I mean, it just is kind of like it's just coincidental that this turned out to be nice somehow. Yeah, that it just turned out to be a geometric series. If it didn't turn out, then you had to have that coefficient multiplication in the front. That would make it like much harder. Okay, you got n minus 1, and then x upon 3 power 1, and then x upon 4 power n minus 2, and then x upon 3 power, well, 2, and so on, right? Yeah, exactly. So this is almost like 1 upon 4 power n, and then you got 1 upon 4 power n minus 1, 1 upon 3 power 1, and so on, till you eventually get 1 upon 3 power n. This is our coefficient, but that times 1 upon 12, of course. Yeah, isn't that right? So what we can do is just multiply this by 1 upon 3 minus 1 upon 4 and divide by the same thing. So then this will just turn out to be 1 upon 3 power n plus 1 minus 1 upon 4 power n plus 1, and that upon, well, 1 upon 3 minus 1 upon 4 is just 1 upon 12. Ha! Nice, isn't it? This cancels. Wow. This was unexpected. It's cancelled out. So this is it. This is our coefficient. Yeah. So now you have second one. This is going to be 1 upon 3 power n plus 1 minus 1 upon 4 power n plus 1. Cool. Okay, let's go to third. If x is so small that the square and higher powers of x can be neglected, and this is equal to 1 plus kx, then find the value of k. Okay, so all right, no big deal. This is 1 minus 4x to the power of, so square and higher powers can be neglected completely. That's really nice. Negative 5.2. Then you can just, I mean, approximate it. So 1 minus 2x to the power of negative 1 upon 2. You can just approximate it to infinity. Okay, cool. So it's gonna be 1. This 2 cancels with that, so negative, positive, and then you got 5 times 2, 10. So 1 plus 10x, just that. No x squared involved, okay? And then you got 1 plus x. That's it, really. It's gonna be 1 plus 11x, and then the 10x square that would have been there, but now it's not. Actual neglected. There we go. This thing is just equal to 1 plus 11x to a first degree approximation. Cool. So k is just 11. Yeah, makes sense. Cool. Next question. Fourth question. Find the quotient of x power 25 and the expansion of this. Oh, wow. Oh, so this is that, right. I think I have encountered one such question before. But this was not in binomial, it was in combinatorics. But anyway, this is also doable. So just multiply by 1 minus x on both sides, sorry, on numerator and denominator. So just get 1 minus x upon 1 minus x power 5. And then that says 1 minus x into 1 minus x power 5 to the power of negative 1. So this will just not be 1 minus x, and then it will be like 1 plus x power 5 plus x power 10, whatever. And you just want to the power of 24. So thing is, this x, it just makes it like 5k plus 1. That will be the power of x. And yeah, that's not good. That will just give us 26, not 25. So 25 is only when you have 1 times something over here. Exactly. So there we go. The question is just 1. Exactly. Okay. Next. Fifth. Find the what first negative term in the expansion of 1 plus 3 up 3/4 of x to the power of 13 upon 3. So first negative term in the expansion. Also find the range of the values of x for which the expansion exists. Oh yeah, sorry. Range of values of x for which this expansion exists. Uh, huh. You mean like what? For which the expansion exists? I've never seen that before. So you mean for some values of x, your series will be divergent? Is that for real? I mean, in the denominator you have some kind of like a factorial, and on the numerator you just have a polynomial, so it wouldn't converge, right? So it wouldn't diverge, right? In the end, it's got to converge. So why should we expect this to have a range of values for which I mean, for which this exists? Hmm. This is weird. Uh, no, I don't know. Okay, I don't know. For what values of x should this? Ah. Okay, so let's look at the pattern of these binomial coefficients. So you have something like 13 upon 3 minus 1. So yeah, first you just have 13 upon 3, and then you have this minus 1 that times itself. So 13 into 10, and that upon 3 power 2, but that times 2 factorial as well. Okay, and then you got x power something, whatever. And then this keeps on going, right? Ah. Oh, okay. Well, I'm starting to understand what's happening. Each time you just have like the magnitude of the coefficient is increasing by 1. Yeah, except okay, this might just diverge, right? So let's keep on going, and let's see if at some point this will actually start to get numbers which are not good, right? So first of all, just got 13 upon 3. Okay, I'm gonna add an x over there as well. Okay, first of all, just this upon 1. Okay, that times x. So x power 1, right? Then you have this minus 3. So 10 upon 3, and then upon 2. So x power 2, and then so on. So third, like it's gonna be what? 6 upon 3. Then you got, sorry, it's going to be 7 upon 3. What am I doing? And then you got this minus 3 is this upon 3, of course, and that would have x power 3 over there. And so notice that each of these times is just increasing by x, right? So your ratio, that will be like x times this kind of number, and that upon this kind of number, right? Okay, let's keep on going. Let's subtract once again. So you just get 4 upon 3, then you get 1 upon 3. So upon 3 upon 3, all right. So till now nothing bad is happening, it's just all really small, but the thing is this is finite. Okay, that's the main thing, this is finite. Okay, cool. And just let's not think about this for a while. Oh, it should be 4 and 5, sorry, it should be 4 and 5. And now this will start. Okay, so the first question is really very easy to answer, and I was not solving for the first question, I was solving for the second question, but still. So the thing is like 1, 2, 3, 4, 5, the sixth thing. So the C6 term, right? Negative, it's not negative, is it? It's 13 upon 3. C6 term. that term will be the first negative term. So the seventh term will be the first negative term, right? So fifth, seventh term, and for what values of x will this actually converge, right? So till now, nothing bad is happening. Now, you will start increasing by 1, so it's going to be like upon 6, and then it's going to be negative 2/3. Still, nothing bad. Now, it's going to be negative. But remember, you're always multiplying by x, by the way, okay? Yeah, you're always multiplying by x. And now it will start, I mean, this will start incrementing by 1, and this will also start incrementing by 1. Right, that's what's going to happen. So in the end, as these values, I mean, start getting bigger and bigger in magnitude, of course. So now, till now it was decreasing, and now it will start to get bigger. So this will be negative 5/3, and then that upon 7, and then you got negative 8/3, and that upon 7, and so on, right? So you can see this is getting bigger by 1 every, I mean, the step is just 1, and over here the step is also 1, right? The magnitude that's getting bigger than 1. Yeah, so in the end it's going to be like some really big number plus some small number that was basically like, yeah, 13/3. So negative, basically negative of some very big number and plus 13/3, and then you got the same big number and that plus 1, right? So as k approaches infinity, this whole thing just approaches -1. Yeah. So what that would mean is that, well, whenever this 3/4 x, so actually I said x power something, but it's supposed to be 3/4 x to power that, right? Because I messed up that 3/4 over here. So yeah, if that, so it approaches 1, and now the main thing is that every time you go from one to another, you're also multiplying by 3/4x, right? So if somehow 3/4x is more than 1, we are doomed, because now these numbers that you're multiplying with, right, those contain that 3/4x and something which is approaching 1, so -1, but yeah, you get it, right? So that means your coefficients are now increasing, and they are increasing till what? Till infinity. The whole series will diverge in that way, right? And that's a problematic thing. So you don't want that to happen, and that's why this thing 3/4x, it should be its magnitude at least. That should be less than 1, right? So x should belong to -4/3 to 4/3 for this to actually work. Yeah. Also find the range of values of x for which this expression exists. So in fact, I mean, you could just apply this to any kind of exponent and it will still work, most likely. Yeah. Right. Yeah. It should make sense. Okay, let's go to 6th. Prove that this thing equals this thing. Oh, come on, seriously. Just two geometric progressions. It's like 1/1 plus x. That times of 1/1 plus x is equal to 1/1 plus x squared. What kind of joke is this? So 6 is done. You don't even need GPT for this. Okay, 7th. Evaluate this limit. Right, cool. So yeah, of course. Well, I think I've seen a similar limit once, right? But first of all, as x approaches 0, this approaches 1 and whatnot. So you could just take something out, right? So this will be like, I'm just gonna take square root of 1 plus x out from this upper stuff. So this will just be 1. I mean, that approaches 1 anyway. So just 1 minus of 1 plus x to the power of, well, 1/3 minus 1/2, which is -1/6. That upon, so 1 minus of 1 plus x to the power of 1/4 minus 1/3, which is 1/12, -1/12, yes. And now think about it, this thing is just the square of this, is right? Isn't that correct? So this actually can just be written as 1 minus of 1 plus x power -1/12, and then you got this times of 1 plus 1 plus x to the power of 1 -1/12, right? I know they don't want us to be doing it like that, but whatever. If you have an easier solution, why not use that? So this cancels, right? Yeah, and then you just got this thing. That's it. And then x approaches 0. This thing just approaches 1. So it's just 1 plus 1, 2. Awesome. Wow. 7th done. Let's go to 8th. Find a and b so that the coefficient of x power n in the expansion of this, okay, maybe 2n plus 1. Find a and b so that the coefficient of x power n in the expansion of a plus bx upon 1 minus x squared, maybe 2n plus 1. What? Okay. Fine. No big deal. It's not n in this expansion, maybe 2n plus 1. I mean, actually it's like not so good. The usual way of just doing a plus b and fine, let's just do it. Okay, whatever. It's got a plus bx, then you got 1 minus x power negative 2, right? X power n, right? Actually 2n plus 1, okay? So it's gonna be like 1 minus of negative. Okay, let's just figure out what this series is actually. So 1, then it's gonna have minus x, but then you got it's like plus 2x, and then plus, so negative 2, negative 3, and then that upon 2. So well, that 2 cancels the other 2, so it's just gonna be 3x, and then plus, and then of course there's negative and everything, but that got squared anyways, so it's 2x squared. And then you got negative 2, negative 2, negative 3, negative 4, and you got, well, negative 2, negative 3, like that. So this cancels. Perfect. Oh, it's not actually negative, it's supposed to be positive, sorry. And then this times of negative x cubed, and that's why it's still positive, so it's yeah, it's not alternating. It's just only 4x cubed, and now you can see the pattern, right? So it just keeps on going. Okay, cool. You just got a plus bx. We just want the x power n thing, right? So these have the general term n minus 1, sorry, no, n plus 1 x power n. So what you gotta do is just have n x power n minus 1 multiplied by bx. So b times of n, okay, plus, and then a times of n plus 1, right? This should be just 2n plus 1, right? So there we go. A plus b is equal to 2 and a is equal to 1. Well, okay, this is really nice. It just means b is equal to 1 as well. So there we go. A is equal to b equal to 1. So this is true for every single n value, right? Then this must happen. There we go. A is equal to b is equal to 1. Okay, 8th done. So the 9th. Assuming that x is so small that exponent high powers of x can be neglected, if this is equal to this, then find the value of p and q. Fine, linearize this thing. I get it. So, well, that's just negative 4. It's gonna be 1 minus 3x. And this guy is just, well, it's 1 upon 2, right? Oh, you got a 16 over there. Take that out. Take that out before doing anything. So 4, and then you got 1 minus of 3x upon 16, but half of that actually. So 1 minus 3 upon 32x. And then you got x plus 8 to the power of negative 2 upon 3. So take that 8 out. Just get 4. Oh, it should be 4 over here, sorry. Okay. And then you just have, well, 1 plus x upon 8 to the power of negative 2 upon 3. So yeah, to do that thing, it just becomes negative x upon 12, right? Because 1 upon 8, 2 upon 3, yes. That's what it's gonna be. This cancels. Perfect. It's just gonna be 1 minus all of these added up, because you know the sum of roots and all that stuff. Yes. Right, 1 and 1 from here, negative x upon 12 from, yeah, just all of these added up. So let's look at it. 3 upon 32 plus 1 upon, oh, this is really bad. 3 plus 3 upon 32 plus 1 upon 12. It's a multiple of 4. It's a multiple of 4. But I multiply by 3. So 3 plus 9 upon 96. plus, well, got multiplied by, now what is 96? 8? Yeah, 8. 8 upon 96. So this will be 3 plus 17 upon 96. That's going to be 17 plus 12 times that. So it's 27 and 18 to 88. And plus 17, I guess. Is that correct? 27, 80. Yes. So it's going to be 200 and, well, okay, that's not here. 305. That's the thing. 305 upon 96. And for some reason they have 61 over here. Not a thing. Why? Why do they do this? 61. Why? How is this looking like 61 to you? P and Q? What? This isn't obvious to me at all. Why should this happen? It's negative right there. It's 1 upon 2. It's negative 4 over there. I mean, this works out perfectly. This they cancels, right? It's just 1 upon 2. And yeah, everything works out perfectly, but then in the end, it's not matching up. Then that's negative 3x for sure. And that's also just negative 3 upon 32x for sure. And so it should be 3 plus 1, 1.12 plus 3 upon 32 and whatever. So it should be 9 upon 96 plus 8 upon 96. So 17 upon 96. 3 times of that. Okay, so if that's the case, let's do it. 288 upon, oh wait, it's supposed to be 305, sorry. So 305 upon 96 is equal to 24p upon 61q. That's it, huh? Let's do it. I know, this is just really bad. Doesn't look like that at all. Okay. Let's figure out what this is going to be. Okay. So q upon p is equal to, I'll just go with p upon q, whatever. 61 times this thing upon 24 times that. How is this helping? 305 into 61 upon. Oh, it's the complete opposite of the thing. I mean, like 61. Oh, 61 times 5 is 305. Okay. Okay, fine. What? But what is this? Now this is just stupid. X1 and hyperbox can be neglected, of course. You just neglected that anyway. This should actually work out. Why didn't it work out? There was 4 there for sure, and everything was going correctly. It's not working out. What the hell? Find P and Q. Wow. We got 96 into 24. What kind of sick joke is this? This is it, huh? Fine. So P is really just 305 times 61. If it's not this, I'm just gonna say it's wrong, right? Their question was wrong. And then Q was 96 into 24. This is it. Next. So this is done, huh? Let's check it. Oh, okay, 10th, 11th, 12th as well. Fine, let's do 12. Let's do this thing now. If x is nearly equal to 1, then prove that this is okay, 1 upon 1 minus x nearly, or so x is nearly equal to 1, huh? Okay, cool. So limit as x tends to 1 of this is equal to 1 upon. Look, first of all, that's not how limit works. Okay, these people are just dumb. They don't understand how limits work. You can just do that. No, that's just stupid. Okay, whatever. So you got a x power b minus b x power a upon x power b minus x power a. What? Are you serious? Okay, let's do this thing. So let's just say that x is 1 minus h. Okay, cool. So then this whole thing, it just becomes like, yeah, just trying to prove that this is approximately 1 upon h, right? Okay, so ax power b, that's going to be a times of this thing power b, which is like a into 1 minus of bh basically, and then minus of, well, this thing is just going to be minus b times of 1 minus ah, and then x power b minus x power a, right? This is frustrating. It's going to be 1 minus of bh minus of 1 minus of ah, which will be basically just a minus b times h. So let's look at it. It's going to be a minus b common, and well, yeah, this actually just cancels, so it's just going to be a minus b upon a minus b times h. So this cancels, yes. So the first thing is very much correct. It's this thing nearly, yeah, but this makes no sense. Okay, this is not correct at all. This is just really wrong. So yeah, there we go. So 10th proved, although this is just bullshit, right? This should not happen. Sum the series 1 plus 1 upon 3 plus 1 times 3 upon 3 times 6, and okay, whatever. Okay, 3, 6, 9. Look at the pattern. It's like all multiples of 3, huh? What if you take that 3 out? Then it's just 1. 1 times 2, 1 times. Okay, of course, it makes sense. So this will be like 1 plus, well, 1/3 plus 1/3 squared, and you got 1 times of 3, and that. So the difference is of 2, right? So why not just put 2/3 right there? Okay, this is gonna make sense. It's gonna make much more sense now. So what we'll do is just write it as 1 plus 2/3 of 3 upon 2. Sorry, no. 1 upon 2, sorry. And then you got plus 2/3 squared, and then you just got 1 upon 2 and 3 upon 2. Wow, that's weird. Oh, so just put negative over here as well. Now it makes sense. Okay, it's got negative, and then in the denominator it's got 1 into 2, and you can see the pattern already, right? The next one is just negative 2/3 cube, right? And then you just got negative 1 upon 2, negative 3 upon 2, negative 5 upon 10, then in the denominator it's got 1 into 2 into 3, and so on. So you get the idea what this is actually. It's just yeah, it's just 1 minus 2/3 to the power of negative 1 upon 2. That should be it. Exactly. So it's just 1/3 power of negative 1 upon 2, which is like 3 power 1 upon 2, which is just square root 2. Yeah, so it's square root 3, sorry. So this sum is just square root 3. So is this like a proof of square root 3 is rational? No, it's not. It's an infinite series. Okay, infinite series does not, I mean, it represents a never-ending thing, and that's why square root 3 is not rational. Okay, this does not prove that square root 3 is rational. Okay, 12. The value of an infinite sum 1 minus 1 upon 8 plus 1 upon 8 times. Okay, come on. What's this 3 upon 16? Just gave me 3 terms and you expect me to find out what this is, huh? 3 upon 16. What? Oh, so it's like 8 times 1, 8 times 2. Okay. And over there, the difference is of, well, 2. So, understandable. 1 plus 1 upon 8 power 1, right? You also need that 2 right there, so we'll add that in there. So 2 upon 8, which is basically like 1 upon 4 power 1, and then it's gonna be 1 upon 2. Sorry, it should actually be like, let's just go with negative 1 upon 2, right? Yep, that should do it. So negative 1 upon 2 and that upon 1 factorial. This was 0 factorial, that's 1 factorial. It works out. Okay, the next term is just 1 upon 4 power 2. And we got negative 1 upon 2 into negative 3 upon 2 and that upon 2 factorial. That should do it. And so on. Yes, so it's just 1 plus 1/4 to the, what the hell? 1 plus 1/4 to the power of negative 1 upon 2. That is the thing. Yes. So 5/4 to the power of negative 1 upon 2. That's like 4/5 to the square root of that. So 2 upon square root of 5. That's the answer. Man, these series are fun. It's much better than what we did in the last video though, because that was just torture. So much of calculation and whatnot. Okay, this is nice. So 12 done. So yeah, that's supposed to be C. Now let's check the questions, the answers. Sorry. There we go. Second is what? 1 upon 2 of 1 up what? No, please, that's not right. It can't be right. Okay, third 11th is correct. Fourth 1, 5. What is this? What is this value? So x is no, it's not between 0 and 4 third. It's between negative 4 third and 4 third, right? And this, oh yeah, like it's 7th term. Okay, that actually at least was correct. So these are correct. 6th didn't do anything. The 7th is 2. Yes. 8th. Okay. And yeah, 4th. This is like whatever this was. I think what happened is that they printed this upside down. So it should have been 61 upon 24. That would have made perfect sense. Like because 24 times what was the Q value? 4. So 24 times 4. Sorry, yeah, 24 times 4 is just 96, and that's why this thing. Yeah, so it would have made perfect sense if this was reciprocated, but didn't do it. So 9th, my answer is correct. Okay, that's it. 10th. Okay, 10th was a proof question. Then 11th, square root 3, and then C. Okay, cool. This is correct and this is correct. Only correct incorrect one was second. So they are saying it's 1 upon 2 times 1 minus 1 upon 3 power n plus 1. I don't see how that's correct. So what question was this? Second, right? Where did the first question go? Okay, first question was actually much easier, so I didn't write it down. Okay, find the question of x power n in the expansion of this thing. So, oh, wait. Okay, now I understand where I messed up. It's supposed to be x minus, it's supposed to be 3 minus x and 1 minus x right there. So these are of negative 1. So it's supposed to be 1 upon 3, and then you got 1 minus of x upon 3, and then you got 1 minus of negative 1, of course. Y upon, sorry, x, just like that. That's gonna be 1 upon 3, and then you got 1 plus x upon 3 and all that stuff, right? That's how it should have been. So, oh yeah, actually, what I took was this thing, right? I took this, which is of course wrong. I don't know, why did I take that? This makes like no sense. Why would I do something like this? Okay, fine. So that went wrong. Although that was actually enjoyable, but this is wrong. Okay, fine. So next part is multinomial theorem for natural index. This is something that I already told you about. Number of distinct terms in the expansion of this is, well, n plus r minus 1 c r minus 1. Right, so it's from a star bar theorem, and honestly, explaining it right now will be like not good. Sum of all coefficients in is obtained by substituting all the variable terms unity. Isn't that just obvious? We have been using that for so many questions, right? Why give it now? Greatest coefficient expansion of this is n factorial upon alpha factorial to the power of m. So this is new. Okay, this I didn't know about. Or maybe I just forgot about this. So alpha factorial power m minus b, and then alpha plus 1 factorial power b. What? That's the greatest coefficient in the expansion of this guy. So it's like r of these. What's m right there? I don't understand what's m. N gonna make sense, but where alpha is the quotient and beta is the remainder when n is divided by r. This is new. Alpha. Okay, first of all, where is alpha? I can only see an m and a beta. I cannot see alpha. Maybe that m is. Oh, so this is the alpha. Sorry. Okay, now I understand what alpha is. Fine. So alpha is the quotient when it's divided by r, and beta is the remainder. In what is m? Most likely it's just n, but they wrote it differently. Yeah, or maybe like this is like till r they said, but maybe it was till m. I don't know. I have no idea. Okay, and if n is positive integer and these belong to complex numbers, and the quotient of x power m in the expansion of this is. Isn't this the same thing though? Why tell this now? And what are these alpha? Okay, these are non-negative integers subject to the following conditions: that their addition must be n, and okay, this is equal to m. So these I don't know. I have never seen this before. This is multinomial theorem for natural index, whatever. Fine, let's do this exercise now. If I've never seen something, that means I've not ever used it as well. Because generally the things that I use in maths, well, I have been using that for a while, right? So if I've not seen something anywhere, that means it's not that useful. But let's do it anyway. First, find the number of terms in the expansion of, well, this thing, x plus 3y power 2, and then 9x squared plus y squared minus 6xy. But isn't that just binomial theorem? Oh, it is multinomial theorem. Okay. So number of terms in the expansion of this guy, huh? What, isn't this something like finding the degree of the polynomial? Right? Yeah, wait. That's how it is? Okay. So, well, this thing, you can write it slightly differently. You can write this thing as, well, it's like x plus 3y. Then you got 3x minus y. And then 3x plus y. All of that to the power of 3, right? All of this power of 3. When you do the cube thing, over here you will have something like a y cube. Over here you will have a y cube once again. And over here you will have a y cube. Yes. And yeah, of course, it is. That negative thing is the problematic. Like, it's really problematic. Oh, it's not. Okay, this is wrong. This is just really wrong. It should just be square of that. Sorry. So this thing squared double of 3. Okay. It's only x plus 3y to the power of 3, and then you got 3x minus y to the power of 6, huh? This might look like a 6th degree polynomial, right? I mean, yeah, got 7 terms. Yes, this has got 3 terms. Now my question is, will all the terms survive when we do the x plus y to the power of 3 thing? Maybe or maybe not, actually. It's kind of complicated, isn't it? Number of terms in this thing. I just fear that some terms might not survive. Okay. You could, like just, oh wait, it's square. Why? Oh, come on. You should have told me that already. Square of that. Okay, then this might make sense. So, okay, cool. Now think about it. What can we do? We'll definitely just take out 3x squared from this. So this will be like 3x squared, that's the power of 6. And then you've got 1 plus 3y upon x, and that times of 1 minus 3y upon x to the power of 6. Oh, it's supposed to be, no, it's supposed to be y upon 3x, sorry. Alright, and now we need to figure out how many terms. Just use y upon x as, I don't know, a. Then this will just be 1 plus 3a, and that times of 1 minus a upon 3. All of that to the power of negative 6. Sorry, positive 6. Yes. Some of these terms might be there and some might not be. What kind of terms will be there? The main problem is that there might be cancellation happening, and that will just, yeah, that really is problematic. I don't want cancellation happening, okay? Just don't want that to happen. Think. When will a term get cancelled? Wait. When does a term get cancelled actually? We don't know. We just... we don't know that. This is bad. This is really bad. Okay, you could just, like, expand this, so this will be like 1. 3 minus 1 upon 3, that's just going to be... Well, yeah, it's got 1 minus 1 is like 8, so plus 8 third of a. You got minus a squared, so minus a squared, just minus a squared. That power of 6, yeah. The highest power is definitely just 12. Yes, that's understandable, of course. But are all the other powers here as well? I mean, you got this negative thing over here that just annoys me, and it's not. How do I solve this? Number of terms in the expansion of this. Can't I just say it's 12 terms because the degree is 12? No, that would be wrong, right? It's not 12, of course, but what about the terms in between? So, okay, think. Multinomial coefficient, you say. So this is like 1. So if a has, so this term has power of m in the general term, and this has power of n. So this will be like m plus 2n, right? Is equal to whatever the power of a thing should be. Yeah. Yeah, whatever that thing is. Okay. Yeah. I'm getting of a particular term or something. It's getting complicated. So, for example, this was 1, then you would have solutions for that happening, and but that is a very long method. That's not worth doing. This makes no sense combinatorically as well, right? Yeah, that doesn't make any sense. So you got to do it in some other way. Come on, think. Just if there was something like can we say for sure that terms won't get cancelled? But I think we cannot say that for sure. This alone, I mean, multinomial theorem alone is not sufficient to actually solve this. Of course, you can go by the longer, more tedious method because it's just the power of 6. So what could go wrong, right? Just 6 of these things. Yeah, that's not good. Just have to solve this thing and see what we get. So, for example, the degree 12 term that will be there, the degree 11 term will be there, so on. What term won't be there? I don't know. If I say use a square, as a single thing and this whole thing as a single thing and then use a binomial theorem on this guy, then I might get an expansion. Yes, that is, I mean, that can be done, sure. So you just get all of the even powers first and all of the odd powers the next, right? But then which of these pair up and cancel each other? That is a hard question. So, okay, we'll leave that for the next video because I've never seen this before. But fine, just leave that. I can't say it's 12 for sure, okay? And most likely that's also not the answer because it was not, if it was that simple, they would not put this question here. Okay, find the question of x power 3, y power 4 and z power 2 in the expansion of this. Yeah, the expansion of 2x minus 3y plus 4z power oh, this is actually much easier than before. Fine, it's going to be n factorial upon, so x needs 3 and that means 4 and that needs 2, so that when added up it's supposed to be 9. Yes, it works out. So 2x power 3 or there's like 3 factorial, you got 4 factorial, 2 factorial, and then it's got 2 power 3, negative 3 power 4, which is just 3 power 4, and then 4 power 2, yes, it's just 2 power 4, yes, so it's supposed to be 2 power 7. And that's like 2 power 6. Okay, cool. Let's try to do it. So 9 into 8 into 7 into 6 into 5 till that only. Now the 4 factorial is just not here. 3 into 2 into 1. Okay, why did I write that? That times 3 power 4. So this cancels with that. Cool. This is just 40. So 40 into 9 into 7 into 3 power 4. That will be the thing. So this is just 40 into 3 power 6 into 7. That should be the thing. Yes. So that's the coefficient. 7, it's like 280 into 3 power 6. Yes. Let's go to the next question. So third question is find the question of x power 3 and the expansion of this thing. So 1 minus 2x plus 3x squared minus 4x cube. Ooh, that's just not good. What is this? 1 upon 2. Okay, this is different. Oh. Huh. Hey, okay, we could actually, think about factorizing this thing, right? Because, yeah, maybe, just maybe we can do that. So, what I'm thinking is like 1 plus x minus 3x. No, that won't work. This won't work. Oof. I thought it would work. It wouldn't. That would 4 for that. What if it tried and somehow did work though? Isn't it worth the risk? So 1 minus x. Then I'll just leave, I don't know, minus x squared, which is like 4x squared minus 4x cubed. So this will be 1 minus x, we got, and then minus x into x plus 1. Yeah, this is getting bad. And then plus 4x squared into minus x. So this will be like 1 minus x times 1 plus 4x squared, and doesn't work. Some other way of doing it, of course. So just want x power 3. Oh, okay, that's actually not that bad. So to the power of 1 upon 2, you say? So just use the general binomial theorem and feed this thing as the x value, right? That might work. Or yeah, like, okay, that can work really. So let's try it out. So to the power of 3, after that term, it's not worth looking for it anymore. But before that, we could look for it and we will see what we get. So first you just have 1 and then you have plus 1 upon 2 and this thing. So 2 minus 2x plus 3x squared minus 4x cubed. Okay, and then you have 1 upon 2 minus 1, it's like negative 1 upon 4, but it's negative 1 upon 8. Negative 2x plus 3x squared minus 4x cubed, that power of 2. And then you got, well, negative 3 upon 2 over here added up. So it's going to be 3 upon 8. 3 upon 8, but that upon 3 times 2. So 1 upon 16. 1 upon 16. And then you got minus 2x plus 3x squared minus 4x cubed, and that power of 3. Yes? Now, this thing, it's the cube term will be just negative 2 power 3, so it's supposed to be negative 8. That's why it's going to be negative 1 upon 2 right here. X cube. There we go. Cool. From here, what x cube term do you get? You can just have this thing directly, right? You will have like this times that or something, right? Wait, okay, you cannot have this. Yes, you have to choose something else from the other bracket. Otherwise, this would make no sense, right? Yeah. Oh, yeah. Oh, you can write this differently. You can write this as negative 1 upon 8 times x squared, and that times of all of this stuff. So 2 minus 3x plus 4x squared, that's power of 2. So, alright, now we can do it. So like x squared must be combined with x, and x must be combined with x squared, and that's why 2 times of that thing. So 2 times of negative 12. Yeah. That's how it's gonna be. Of course, that's the only way this can be. So it's got no x cube term, so just have to rely on that. Yes. I mean, I'm thinking of 2 brackets and then choosing 1 term for each bracket. That's what I'm doing, alright? So that will just give us 2 times of negative 12x cube, right? Oh, you don't want x cube, you just want the x term over here. Oh, that's different. So just for the x term, there's only one way, one constant and one linear, right? So that would be negative 12, so negative 6, and that times 2, so negative 12. So negative 12x is what we will get from here. So then this will just be 12 upon 8, which is 3 upon 2 x cube. Okay, so that's done. You don't need this anymore. Finally, from here, the x cube term is just, I mean, only this thing, of course. So that is negative 2x cube. Cool. Now 3 upon 2 minus 1 upon 2 is just 2 upon 2 is like 1. So x cube and then minus 2x cube, so it's going to be negative x cube. And that means the coefficient of x cube in this expansion is negative 1. So third, negative 1. Let's go to fourth. If the sum of the coefficient in the expansion of this vanishes, then find the value of alpha. Sum of the coefficients in the expansion of this. Just put x is equal to 1. Why not do that, huh? Yeah, because that will just get rid of these x things and just put, yeah, so that should make sense. Then what you get is like alpha squared minus 2 alpha plus 1, that to the power of 51. That just becomes, well, 0. So yeah, this is happening. So alpha is equal to 1. This was easy. Okay, let's go to fifth. What is the coefficient of x power 3 in the expansion of 2 minus x plus 3x squared power 5? Can't believe this is still happening. Oh, come on. Fine. No big deal. You could use binomial theorem, yes, or you could use multinomial theorem. Multinomial theorem is like better to use, I think. So just the x squared power 0, x squared power 1, x squared power 2 things will work. Actually, x squared power 2 won't work. So first, x squared power 0. In that case, what is the x power 3 term? That will just be 5c. I'll just go with 5 factorial. 5 factorial upon, I mean, it's going to be 3, of course. So you got 3 factorial, 2 factorial, and then you got 2 power 2, and then negative x power 3. Okay. If this xy is not here. If it is there, it can only be once. That means from, yeah, right, just once. That means like 5 factorial upon 1 factorial, and then if that is there once, this x must also be just once. So 1 factorial, and then got the remaining stuff, which is 3 factorial. And then you have 2 power 3 negative x power 1, and then 3x squared power 1. That's right, that's the x cube terms. So fancy to is just 5 into 4 upon 2, which is 10. So this is just 10 times 4, which is like 40. So it's negative 40x cubed, first term, right? And what about this guy? It's like 5 factorial upon 3 factorial, which is just 5 into 4. So that's 20. So 20 times, what is this thing? 8. 20 times 8 is 160, right? 160, that times 3 is like 480. So you got 480, and then it's negative, positive, negative. Plus, yes, negative, and you got x cube right there. So it's supposed to be negative 520 x cube. That should be it. So fifth done. It is negative 520. That's the coefficient. Hopefully. Yeah. Let's look at the answers. So first 13. So it's not. Wait, what? Okay, this is weird. I thought it would not be 13. Okay, I mean, this is, of course, I mean, it's a 12th degree polynomial in x and y. Yes. But all of the terms existed. How can we say that for sure? I don't know. Okay, second is this 9 factorial upon 3 factorial, 4 factorial. Yeah. Which I actually calculated. So, come on, they didn't even take the effort of doing it. Yeah, right, that's right. Okay. And then third is negative 1. And then fourth is 1. And this is 5. Why is this negative? It's not negative. But it's supposed to be negative, right? It's cube. Yeah, right. It's supposed to be negative. In both of the cases. I don't understand this. Right, whatever. At least the magnitude was correct. So I'll give this the correct. Fine. So injected exercise fourth done. Next is what? Binomial coefficient. We already were using binomial coefficient all the time. And you are introducing this now? Why? Why? This is so stupid. Why introduce this now, not at the front? Okay. Oh, come on. Are you serious? Like, this is the easiest part of the whole thing. That greatest term and all that stuff. Man, that is not the easiest part. Why did you not put this in the front? Whatever. Fine. And it's just a series of final coefficients. And you got this exercise, and oh yeah, that thing. I even made a video on this thing. Whatever. Okay, whatever. Then you got access one. Okay. Fine. So I'll stop here. See you guys in the next video.